Okay, so last week of class. So today we're going to talk about phase transitions, and we're going to work through the Ising model. We're going to very quickly go through the Ising model, and then I'm going to show you how to solve it using mean field theory. And although mean field theory is usually disparaged, and people say, well, what's the point of learning mean field theory when normalization group's so much better, and so on and so forth. Actually, you can get an amazingly long way with mean field theory, much more than people normally give it credit for. And so we're going to just do that as a sort of prelude to those of you who want to go on and take phase transitions in the normalization group course in a future year. So the thing we're going to be learning, we're going to be using is self-consistent mean field theory, which we already saw was useful in analyzing many body theory. We used it last week to study charge systems, and today we're going to use it to study phase transitions. So this is all in section 3.4 of the written notes. So I'm going to skip all the parts to do with the derivation of the Ising model from quantum mechanics. So in the notes, you'll see that we take a look at quantum spins on a lattice. We basically look at the atomic orbitals and we work out how it is that the energy of the system depends on the orientation of the spins. And then, in fact, I derive the Heisenberg model in those notes, and then the Ising model is a special case of that. So here's the setup shown on the right-hand side. So what we have on the right-hand side is a lattice. There's n lattice sites, and the spins at each lattice site are labeled by SI. They can take two values, plus or minus one. So what we have in mind here is spins, quantum spins, that are spin a half, like electrons, and so therefore they have two states if you choose any direction of quantization, say a direction where there's a magnetic field pointing in the z direction, then there's two values, n is plus or minus 1, or s is plus or minus 1, that we can choose using choosing units appropriately. And we saw halfway through the class when we were looking at the quantum paramagnet that the paramagnetic interaction with an external field is what you can see in the right-hand column. Namely, you take the magnetic moment, so you dot it with the external field. That gives you the energy. The system can lower its energy if the spin is in the same direction as the field. That's all the energetic considerations for the paramagnet. Now, what we're going to add to this Hamiltonian for the Ising model is we're going to add a interaction term. So what does an interaction term mean? Well, what it means is the following. I'm going to write down two spins, Si and Sj, and then there's going to be an interaction which is Jij. So let's just take this apart. So first thing is that this term over here is this term in the energy requires the energy of the spin I and the energy of the spin J. So this is a cooperative effect, cooperative contribution to the Hamiltonian. And what I mean by cooperative, it depends on both the spin I and the spin J. So that's the first term. That's how you know it's an interaction. It's not just something proportional to the spin. It is actually an interaction between them. So then we have this quantity, which I've called Jij. So that's over here. And so Jij, what this is you can think of this as how spin I interacts with spin J. And in general, they may not be nearest neighbors. They may be some arbitrary distance apart. So spin I might be at the lattice position Ri, spin J may be at the lattice position Rj, and so therefore this Jij would be some function of the distance between the two spins. And it may fall off in some particular way. But what we're going to do here is we are going to only assume that spins which are nearest neighbors interact with each other. So this symbol over here, that simply means that that angle IJ, that means nearest neighbors. So I go through the lattice, I sum pairs of spins. They have to be nearest neighbors. So this might be, say, spin I, and this might be spin J. And then if they are interacting with each other, then what that means is that there's some kind of bond between them, Jij, that tells you how much is the energy when they are interacting with each other. And what we are going to then assume is that we're going to assume that Jij is equal to some constant when I and J are nearest neighbors. And 0 otherwise. So that's the form. And this Jij is sometimes known as the exchange interaction. Okay, so that's the setup. So that's the Hamiltonian of the system, and we are going to be only dealing with the classical Ising model. So here we're going to look at the classical Ising model only, and there is a quantum version, and that's not, we're not going to deal with that. So then there's a historical note. So this was developed by Lenz and his student Ising in about, well, actually about 100 years ago, somewhere in 1925, maybe 1926. I've forgotten exactly. And we're going to explore the phase transition in this model. And we're going to see, first of all, is there one? And then we're going to see how to derive it. Once I've done this, I'll then tell you a little bit more about what Lenz and Ising concluded in their study 100 years ago. So let's now write down the full calculation. So our goal is to know if there's a phase transition, and how are we going to answer this question? Well, what we're going to do is we're going to try to compute the partition function. And what is our strategy? So the strategy is the following. First of all, this is a hard problem. And why is it hard? Well, it's hard because the partition function doesn't factorize. So all interaction problems are, by definition, they do not naively factorize. And the way to solve them is to find some dirty trick so that you can factorize them. So what we're going to do is we're going to do a trick to approximately factorize the partition function. So here is our trick. So basically, the trick is to we're going to try to find an effective paramagnetic theory that emulates the interacting theory. And the idea behind that is what we talked about at the end of last lecture. So the idea is, if you look on the left-hand panel, at the bottom there, we have our interacting system. And so the trick is we're going to see, can we replace this whole interacting problem with multiple spins by one spin interacting with an effective field. So this effective paramagnetic theory, what it will look like is a single spin interacting with an effective external field representing the effects of the other spins. And this was why we were going to do that. Well, we know that this strategy was spectacularly successful in the case of the charge system. And so we're going to use that same idea here. So what we did in the charge system was we figured out a way to compute that effective field in a principled way. And so what we have to do is, what we need to do then is to compute this effective field in a principled way. When I say principled, what I mean is that you say at the outset what it is that you're going to do, and you explain what the approximation is, and then you just sort of go and carry that out, and it has built-in safeguards as we'll see. So let's go ahead and do that. So step one is to solve the paramagnetic problem. So for step one, we're going to assume that that J is equal to 0. So in other words, we have a paramagnet. So then we know that the partition function for n spins, because J equals 0 and external field H, we know how to compute that. That's what we did before. It's just the product of the spins at each site. So this is the product from I equals 1 to n of the partition function for one spin. And the partition function for one spin, well, it has two terms, once when the spin is up, once when the spin is down. So that is e to the beta h plus e to the minus beta h. So that's the exact partition function for the paramagnet. And I ask that you check that yourselves just to make sure that you know how to get that. All right. So now let's go on and write down what the result is. So then what we get is Zn of j equals 0, hb non-zero is then 2 cosh h over kbt. And then the whole thing raised to the nth power. And if I want to know what the magnetization is, the magnetization per site that's just m, is the following. I'm going to sum over all the lattice sites, work out the expectation value of the spin, and then divide by the number of lattice sites. So that's the magnetization. And that is minus 1 over n df by dh. Okay, so that's again, if I write down the partition function, f is minus kt log z. So then if I just differentiate with respect to the external field, that then brings down this coupling with the external field, brings down the factor h si that you can see on the left-hand side. And so that is why the magnetization is just equal to that. So that, again, you've seen this before, but I want you to check that you can derive that. Okay, so that's the partition function and the magnetization. So because the spins are either plus or minus 1, so you can think of this as being the number of up spins minus the number of down spins divided by the total number of spins. Okay, so that's the magnetization. So now we just have to compute what it is. So we have to differentiate 2 cosh h over kt, and then we have to take the logarithm and so on. So using f is, as usual, minus kbt times the log of the partition function. Then what we get is that m is equal to 10th of h over kbt. So that's something, again, that you should check and make sure that you can do the simple algebra to get that result. Okay, so that's the easy part, and we've done this before. So step 2 is now we're going to turn on the coupling. J is returning on the interaction. So what's going to happen is the basic idea is that once J is non-zero, then spin I sees, in quotation marks, 2 fields. First field that it sees is the external field, which is just H. The second field that it sees is the field due to its neighboring spins. So we're going to go and compute what that is. But the most important thing to realize is that this field that is due to its neighbors, since the spins are sort of pointing up and have a magnetization per spin, then this field due to its neighbors is going to be proportional to the magnetization per spin. So this field is going to be proportional to m itself, the thing that we're trying to compute. So that's the basic idea. Now, so now let's do this precisely. So the idea for the precise calculation is to write the Hamiltonian in terms of a local field H sub I as follows. So this is how we're going to do it. So my claim is if I take the Hamiltonian, I can write it in this form minus the sum from I equals 1 to n of Si times an external field, And that's what I've just written down here is the paramagnetic interaction. But now we're going to say that this external field also depends on I. So this is the new part. This is not a constant. And in fact, what is this? Well, if I look at what HI is, it is the external field plus the sum over J of Jij times Sj. So this formula is exact. So if you go back and look at the term over here on the left-hand side, so here's our Hamiltonian in the middle of the page. So you can see that if I put this HI into this paramagnetic interaction on the right-hand side, meaning this one over here, and plug this into here, then the H turns out will give me this term, and this term put into here will give me this term. So this is an exact statement of the ferromagnetic and the paramagnetic interactions. Okay, so that's a nice exact statement. So how does that help us? So now I'm going to do another trick. I'm going to then write. So that's that. So this so far is exact. Then step 3. I'm going to write in terms of the expectation value of J. Okay, so what do I mean by that? So what I mean is something quite simple. I'm going to write HI is equal to H. And then I'm going to take this, exactly this term here, but I'm going to add and subtract a term that's been very cleverly chosen. The term I'm going to add and subtract is equal to 0. But I'm going to put it into my equation in a sneaky way. So I'm going to write it like this: sum over J, Jij, the expectation value of Sj, plus the sum over J, Jij times Sj minus the expectation value of Sj. Okay, now can you see that this term here and this term here cancel out? So all I've done is I've done nothing. All I've done is I've just added this term and subtracted it. I've done nothing. And if you ask, well, what is the meaning of this particular term here? So this term is it tells you how much Sj deviates from its mean. And that quantity has a name that's called the fluctuation. So this is, in other words, delta Sj is equal to the fluctuation about the mean and that is equal to Sj minus its average value. So that's what that thing is. Okay, so that's the fluctuation about the mean. And this term over here, this term is the constant external field. And this term over here is the mean field due to the other spins. And it's the mean field because it has the expectation value of Sj in there instead of the actual value. So that's what it is. And so this term is the mean field. And the most important thing about this is after I've done this this calculation, I've just looked over the nearest neighbors. Since this is a constant, this term is not going to depend on I. It's just going to be a constant value for all spins, and so therefore it is equal to a constant. So what that means. Yeah, so that's what that means. My notes here are in the wrong order, which is pretty bad. So yeah, luckily I noticed that. All right. So so far everything is exact. So what is the approximation that we're going to do? The mean field approximation is to ignore the fluctuations. So I told you that this was a principled calculation. So the principled calculation is, see the last term on the right-hand side? We're just going to ignore it. Okay? So we're going to ignore the fluctuation. So we're going to throw that term away. And and later, we're not going to do this in this course, but later it can be shown what is the regime where this approximation is appropriate. And I'll discuss that at the end of the lecture. So now let's now compute just the terms that we have of the first two terms. So now what we're going to be doing is we're just going to be looking at these terms over here, the ones that I've just outlined, and we're going to calculate what that is. So let's have a look at what that term is. So now, so if I want to compute, if I want to compute the second term, suppose we are on a d-dimensional lattice. We're going to say that the lattice is a cubical lattice or hypercubic lattice. Then it looks something like this in 2D. So then the number of nearest neighbors. So here is my spin, and then the nearest neighbors to that spin are this one, this one, this one, and this one. So these are the nearest neighbors. And so how many nearest neighbors are there? Well, so the coordination number is equal to the number of nearest neighbors and that is equal to 2 times the spatial dimension. I'm going to call that coordination number little z. And you can see here that it's in one dimension, there'll just be 2 nearest neighbors, one on either side. In 2 dimensions, there's 4. In 3 dimensions, it's like this, there's 6. So you can see that it's going to be 2D. So now we know that, what that means is that this term, then that HI is equal to the external field plus 2D times the value of the exchange interaction, J, And then the expectation value of the spin is just what we mean by the magnetization. So this term here is the expectation value of SI. They're all the same, and they all have the value M. So now this value is independent of I. And what that means then is that my Hamiltonian is now so I'm going to call this thing H effective. Oh, well, wrong H. Not a Hamiltonian, but an external field, an effective external field. And so now it is then the effective external field times the sum from I equals 1 to N SI. And now we've reduced the problem to a paramagnet. And so therefore, once I've got a paramagnet, then I can straight away say what is the magnetization. So that implies then that the magnetization is the hyperbolic tangent. Let's go back to the formula on this previous page. In the middle here of the page, on the left-hand side, right here, on the left-hand side, what I have is that the magnetization is 10th of the external field over KT, but now our external field is this effective external field over KT. And so that is equal to the hyperbolic tangent of H, the external field, plus 2dJm. And that's the important thing. And so now you can see why this is a self-consistent field. Because, one second, because here I have M, and then M is also here on the right-hand side. And so what I have to do is now, what we need to do is compute M self-consistently so that the right-hand side equals the left-hand side. And you just look at this and it's not obvious that it's going to do that. It's a transcendental equation and so on. So we're going to need how to solve that. Okay, you have a question?
Did you drop the KBT for a reason?
Did I drop the KBT for a reason? Yes, I did. I dropped it for the reason that I made a mistake. So thank you very much. So let's put it in like this. Okay, thank you. All right, so that's a very important mistake to make. So that's our formula. Okay, so now what we're actually interested in is the case. So that's step 3. Step 4 is we want to look at the case when the external field is equal to 0. So what we're trying to understand then is if there's no external magnetic field, we want to understand whether the spin system will spontaneously become magnetic. So the question now that we want to understand is if the external field is equal to 0, can the spins spontaneously self-organize in a cooperative way to create a magnet with non-zero magnetization? So that's the question. All right, so in order to answer that, then what we have to do is set h equal to 0, and then what we get is that m is equal to the hyperbolic tangent of 2djm over kbt. And so that's a transcendental equation. So now we need to solve that. So we're going to solve that graphically because it's we can't solve it exactly. So we're going to solve graphically because it's a transcendental equation. So here's how we do that. So what I'm going to do is I plot a graph of y versus x. So here's y. And then the x-axis is going to be the magnetization itself. So then the first curve that I'm going to plot is the curve y equals m. That's the left-hand side. And then the second curve I'm going to plot is the curve y equals hyperbolic tangent of 2djm. So that looks something like this. And you can see that these curves intersect at the origin. So over here, and so the intersection is at m is equal to 0, and that means, i.e., there is no magnetization. But this solution is not the only solution that we have, because look at the slope at the origin. So the tangent curve is always below the y equals m curve. And so there's no intersections. So you might say, well, maybe if the slope of the origin was greater, then there would be an intersection. Okay, so that's a good idea. So what determines the slope of the origin? So well, to look at the slope of the origin, all we have to do is when m is near 0, then the hyperbolic tangent becomes a linear function. And so in other words, we get that y is equal to 2djm over kbt. And if we want this to be above the straight line, then the slope has to be bigger than 1. We need that. So remember that this curve here, so this is y is equal to m, and then this other part this part is the slope of the origin. So what that means is that if we want it to be above y equals m, then we need this condition to be true. And if that condition is true, what that means is that t has to be less than 2dj over Boltzmann's constant. And I'm going to call that number Tc. So what is it going to look like then if we're in that situation? So let's now draw the same graph that we had before. Okay, so here's the y-axis, here is m, and then I'm going to draw the line y equals m. And now let me draw the hyperbolic tangent curve. So that one now we've set it up, so it's going to be have a slope at the origin greater than the slope of y equals m, but ultimately it's going to have to become a hyperbolic tangent. So what this is going to do is it's going to go through and do something like this. And you can see then, and now we have more solutions. We've got a solution at the origin just like we had before, but now I've also got a solution. I've got this intersection, and I've got this intersection over here. And so these are corresponding values. This is what I'll call m sub s, and this I'll call minus m sub s. And this m sub s is what is known as the spontaneous magnetization. And this occurs when t is less than tc. And I think you can see that intuitively, as t tends to tc from below, then what's going to happen? So the gradient of the origin is getting smaller and smaller. So then the spontaneous magnetization is going to tend towards the origin, and so is going to tend to zero. Okay, so as I make that slope smaller and smaller and smaller, where this point of intersection occurs is going to get smaller. So let me draw you a picture of that. So let's suppose, for example, I had something like this. And then for this example, this one, then the ms minus ms would be like that. They'd be closer to the origin. And we'll say that this ms here, I've drawn it at, say, temperature T2. This is at temperature T2. And in these pictures here, T1 is T2 is less than T1, is bigger than 0, and then both of those are less than Tc. So that's as I get closer and closer to Tc from below, the point where the intersection occurs moves closer to the origin. And so then we can draw the phase diagram, not the phase diagram, we can draw the spontaneous magnetization as a function of temperature. Like this. So what I have is that the spontaneous magnetization is coming down like so, and then it's equal to 0. And this temperature here is Tc, and this value over here is 1, and this is 0. And if I could also have another solution, which looks just like this one, but where the magnetization is negative. In other words, there's a solution on the positive side and a solution on the negative side. Yes.
Is there like some concept of, I don't know, stability, like in a dynamical system here? Like, is there like is it like a pitchfork bifurcation, like where if it's like above TC, it'll like the magnetization will always like the zero will be attractive, and below it, it's like
It is.
repulsive?
It is. It is like a pitchfork bifurcation. So in bifurcation theory, this would be called a supercritical bifurcation, and so it's exactly a pitchfork, because if I were to draw this zero solution, that's always a solution below TC, but this solution, so the m equals 0 solution is unstable at t less than Tc, and it's stable at t greater than Tc, and then the other solutions don't even exist above Tc. So that's exactly what a pitchfork bifurcation is, but this isn't a bifurcation. Okay, the difference is that this is a statistical mechanical system, so we're taking an expectation value of an infinite number of degrees of freedom, and a pitchfork bifurcation is for a single dynamical, one-dimensional degree of freedom. So this resembles pitchfork bifurcation or a one-dimensional dynamical system, but this is infinite number of degrees of freedom, because n is going to infinity, and this is statistical. So it's similar, but it's not exactly the same. And the instability, instability that I drew for t less than Tc, it is unstable, but it's thermodynamically unstable, not linearly unstable like it would be if this was a pitchfork bifurcation. So this unstable behavior is thermodynamically unstable. And we can, I might give you a homework. No, I won't give you a homework. I might give you an exam problem. No, I don't know. I'll talk a little bit about this right now. But anyway, how you compute that instability is from a thing called a susceptibility. Okay. Any other comments about this so far? Okay. So let me just now, the other point I want to make is terminology. So M is an example of an order parameter. So M is equal to 0 in the phase without order. And what is the phase without order? Well, what is that phase? If M is equal to 0, remember that the magnetization is really the difference between the number of spins pointing up and the number of spins pointing down. So what that means is that if M is equal to 0, that means that the expected number of up spins is equal to the expected number of down spins, and so there is no order. There's just some random fluctuations in the system. On the other hand, if I go So that's true for t greater than tc. On the other hand, for m is greater than 0 in the phase with order, where, for example, the expected number of spins pointing up is not equal to the number of spins pointing down. Either one is either it's less than that or bigger than that. And so in that phase, when t is less than tc, we can think of the system as looking something like this, with a low temperature limit. What this means is that over here, let's say all the spins are pointing up, roughly speaking, whereas down here, all the spins are pointing down. And then as I go further and further up in temperature, what happens is some of the spins start to flip, and then by the time I get to Tc, a thermodynamically large number of spins have flipped, so the number of spins that are down and the number of spins that are up is the same, and then the magnetization drops to 0. So that's that is the picture. And remember that m is equal to minus 1 over n df by dh. And so the this varies continuously at Tc. You can see it's a continuous function, but the gradient so what that means is that if you classify phase transitions by the order of derivative of f that is discontinuous, then this will be a second order transition, because dm by dt has a discontinuity at Tc, and so that is d by dt of df by dh, and so that is a second order discontinuity. So that is if you do this, if you classify it. And that if is a very important if, because we don't classify things like that anymore. Okay, back in the 100 years ago, when people didn't know how to deal with fluctuations, that was the way people thought about classifying phase transitions. So in fact, there are many more types of non-analytic behavior than derivative discontinuities. And so what we do today, we would say this is a continuous phase transition. Now, one of the reasons we say that is I'm going to show you some of the discontinuities that actually happen. So now let's talk about what happens next, so this is, I've lost count of how many steps we're on. This is step 4. So now step 5 is examine the behavior near TC. So now what I want to show you is that there are non-analytic behaviors which are very interesting, and so this behavior near TC, this is called critical phenomena, critical point phenomena. TC is equal to the critical temperature. So how are we going to do that? So what I'm going to do is I'm going to do this in the following way. So we're going to define a new variable tau. So dimensionless variable is going to be the critical temperature divided by the actual temperature. And what I'm going to do is I'm going to write down the equation of state, and then we're going to look at that equation of state near the phase transition. So now the strategy write the equation of state in mean field theory. That's the first part. And then the second part is expand near in powers of, eventually it'll be T minus TC over TC near the critical temperature. So that's going to be the strategy. So now let's go ahead and do that. So I'm doing it in this kind of weird way where I'm choosing a variable tau, and then ultimately I'm going to throw away this variable tau and use a different variable. But it turns out the algebra looks a little bit easier for now in the units of tau. So first of all, the critical point, that is h is equal to 0 and tau is equal to 1. So that's the critical temperature, and external magnetic field is equal to 0. So then, and actually, by the way, let me put that in explicitly. In this picture here, our H is equal to 0. There's no external field. Okay, so that's the critical point. So now what I'm going to do is I'm going to take the equation that we just derived. So we know that m is equal to the 10th of m times tau plus h over kBt. So that's the equation. Why is m times tau? Well, remember what we have over here. The critical temperature is on the left-hand side, 2dJ over kB. And so when I write down the equation of state, which you can see now on the left-hand panel, that is h is equal to 10th of h plus 2dJm over kt, which translates into what I have on the right-hand panel. Okay, so that's the exact equation of state. And then I'm going to expand this using the hyperbolic tangent addition formulae. So this then is exactly equal to 10th of h over kt plus 10th of m times tau over 1 plus 10th h over kt times 10th of m tau. So that's an exact statement. And then I can invert this to get h on the left-hand side. So if I do that, then what I find is that I get 10th of H over KT is equal to M minus 10th of M tau divided by 1 minus M 10th of M tau. So that's the exact result. And then I'm going to now then take these hyperbolic tangents and expand. And so what I end up with is the following, and you can check this: H over KBT is equal to M minus M tau minus 1/3 M tau cubed plus higher order terms divided by 1 minus M times M tau minus 1/3 M tau cubed plus higher order terms. I've got to divide those things, and then if I do that, I get M into 1 minus tau plus M cubed into tau minus tau squared plus tau cubed over 3 plus dot, dot, dot. And so that's what that expansion is. So that's the equation of state near TC. And then what I'm interested in is the behavior near the critical point. So I want to look at the behavior when there is no external magnetic field. And then what we want to see is then how does the spontaneous magnetization vary with temperature. So we want to look at the behavior at H equals 0 and the behavior of M for T less than TC. So now if I just set H is equal to 0, then what you find is that MS cubed, sorry, MS squared is equal to 3 times TC minus T over TC. So there's some algebra there. And so what we've learnt is that MS as a function of T goes like TC minus T over TC to the power beta, and this exponent beta is equal to 1/2. So that's the behavior near the critical point. Okay. So what I really want to do is work out other critical exponents. And it would be really great if my notes were in order here. Okay, so this quantity is called a critical exponent. And so there are many critical exponents. For different thermodynamic quantities. Also spatial structure. So also the spatial correlations also have critical exponents, but we're not going to go into those. So let me give you another example other than the magnetization. So I'm going to talk about one that's very important, the isothermal susceptibility. So the isothermal susceptibility, what this tells you is how does the magnetization change when I change the external field. So I take M and then I vary H, and I do this at fixed temperature. So that's called the isothermal susceptibility, and we care about what happens near H is equal to 0 and T tending to Tc from above and below. Okay, so that's the isothermal susceptibility, so this tells us how it answers the question how the magnetization is sensitive to a change in external field. Okay, so let's go ahead and calculate that. So the strategy is quite simple. What you do is you take the equation of state, which is H equals blah, blah, blah. And then you differentiate with respect to H, differentiate with respect to H, use the chain rule, i.e. d by dh of, say, m squared or m cubed is going to equal then 2m dm by dh, which then is equal to chi, bless you, etc. So that's how we're going to do that. So then, if I take the equation of state on the left-hand side and differentiate it, so what I get is 1 over kBt is equal to chi t times 1 minus tau. That's the first term. And then I get some other terms. So I'm going to get 3m squared chi t times tau minus tau squared plus tau cubed over 3 dot dot dot. So that's what I get by differentiating the equation of state. So there's two cases that we want to consider. So the case when t is greater than Tc, then that means that m is equal to 0. So if m is equal to 0, then this term over here vanishes. And so then we get then that chi t is then equal to 1 over kb times t minus Tc. And in terms of the critical exponent, we generally say chi t goes like t minus Tc over Tc to the minus gamma. And then what we've just calculated is that gamma is equal to 1. And that's gamma for temperatures greater than Tc, so I'll put a little plus on it. If we do this for T less than Tc, so then m is not equal to 0. M is given by the formula on the left-hand side. So m is not equal to 0. So now when you do the calculation, so what you're going to find is that chi t is still proportional to 1 over kb times Tc minus t with a different coefficient. And so therefore chi goes like Tc minus t over Tc to the power minus gamma minus and gamma minus is also equal to 1. So then I now plot what we've just calculated. So here is temperature, here is TC, and then what I'm plotting, let me just make this a dotted line. So here is TC, and what we're going to be plotting is the isothermal susceptibility on the y-axis. And so what we've just discovered is that this goes up and diverges with a slope 1 over T minus Tc and comes down with a slope minus 1 over Tc. So what we've discovered then is that the susceptibility diverges to infinity as T tends to Tc, both from above and below. So there's a divergent susceptibility. So what that means is that at Tc, the system is on the threshold of spontaneously ordering to give a m that is non-zero. And so therefore, if you ask the question, what h do we need to provide to make the system order, the answer is that this delta H goes to 0. In other words, if the system is virtually unstable already, the amount of field you need to provide in order to make it align is tiny. And since the susceptibility is delta M over delta H in practice, and delta H is going to 0, then that implies that chi is going to infinity. And that's the physical meaning of this divergent susceptibility. So let me then finish by comparing the results from mean field theory with exact results. So the question then is, how well does it work? So here's what I'm going to do. I'm going to plot beta and gamma. And the first thing I'm going to do is I'm going to show you, write down the result for mean field theory. That's the thing that we just calculated. Then I'm going to show you what is the exact result from Onsager. So Onsager was a genius, and he figured out how to solve the interacting problem in 2D exactly. Okay, and how he did it is amazing, and I'm not going to show you, but then I'm going to show you the result, and then I'm going to show you the result for three dimensions. So that's what we're going to look at. So let's have a look at the values. So the mean field theory, beta is equal to 1/2, and gamma is equal to 1. And I'm not showing you the other critical experiments. For the Ising model, in 2D, beta is actually 1/8, and the exponent gamma is equal to 7/4. So those are exact results. So they're definitely different. It's definitely wrong. On the other hand, if you look at d equals 3, then you find that this number is not a fraction. It's a number like 0.325 or something like that. And this number is about 1.241, something like that. These numbers are obtained by computer simulation, a renormalization group, and so on. And so what you can see from this is that a mean field theory is better in d equals 3 than d equals 2. And if I were to plot up here d equals 5, then this number would be a half, and this number would be 1. So mean field theory is better in d equals 3 than d equals 2, and in fact exact for d greater than 4. In d equals 4, there's logarithms and things like this, so it's not exactly the same. Okay? So as you go to higher dimensions, then mean field theory works better, and that makes sense because in higher dimensions, the spin has more neighbors. Remember, the number of neighbors is 2D. And so therefore, the mean field approximation is better because as for a large number of neighbors, the fluctuations will be less. Okay, so I'm going to finish there. So next time, I'm going to show you one more prediction for mean field theory. And then we'll talk about something else. The anyway, so mean field theory. Mean field theory is giving you very good guides. And I'm going to stop there, but I can see a question. So yeah, what is the question?
Yeah, so in that case, if we define our model not just with like the nearest neighbor, but also like the diagonals,
Yes.
would we expect in 2D like we would like be significantly better?
So very good question. Suppose we had next nearest neighbors as well as nearest neighbors. That's what you're asking, right? Are the exponents different? Right? So it's a great question. And we're going to talk about it next time. But the answer is no. I know, surprising, right? Okay, it's amazing. Okay, and this leads into the topic of universality. And we're going to have to wait until next time to talk about it. Any other questions on today's lecture? Nope. In that case, I'm going to stop the recording.